All right, everybody. So we're going to go ahead and now finally put the critical numbers that we've been talking about together with increasing and decreasing intervals that we talked about after that for the first derivative test. All right, so the first derivative test tells us where and what kind of local extrema exist on a function. Okay, and remember, we're talking about local min or relative. That's the other word we use. So local or relative min or local or relative max. Okay, and so to kind of illustrate what the first derivative test is, we're going to start with a picture of a graph. So let's say we have an xy coordinate plane and we have a function f that looks something like this. Okay, remember, if we draw tangent lines, right, we're increasing here. I'm going to use pink for increasing. We're increasing until we get right about here, where the tangent line has a zero slope, right? Here we have tangent lines that are all increasing. Let me switch to blue. Now, if I start drawing tangent lines, we are decreasing until we get to about this point. Again, here the tangent line is horizontal. And then we increase again after that, right? So the tangent lines have positive slope here. Okay? So remember that if the graph is increasing, that means that the derivative is positive. Whoops, not inverse. Sorry about that. That means that f prime is positive. Right here, where the horizontal, where the tangent line is horizontal, we know that f prime is equal to 0. Same thing here. When the graph is decreasing, the derivative has to be negative. And when we start to increase again over on this side, we know the derivative is positive again. Okay? So using this, anytime we change from positive to negative on the derivative, right? So if the derivative is positive and then it changes to negative, right here we have a relative max, okay? Because it's a high point. So we have a relative max right here. And then here where the graph is decreasing, in other words, if the derivative is negative, 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 and then right here it switches to positive again, now we have a low point. And so this point here would be a relative min. Okay? Now, it's also worth mentioning, too, that we could have graphs that look like this. Okay? This one had critical numbers where the derivative was equal to 0. Remember, we could also have a critical number if the derivative does not exist. Right? So if we have a cusp, we still want to consider those points because here we do have a local min here. Even though the derivative does not exist, right, we still have a local min because we're decreasing, decreasing, decreasing. In other words, the derivative over on this side is negative, 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 and then once we hit 0, once we hit x equals 0, it switches to positive after that. Okay? So let's recap what you need to know. The pictures kind of explain why this is the test, but here's the test itself and how it's going to work. So the summary, let's use green. We have, let's see, we do our number line, for f prime, and we have a critical number. Here on this side, the derivative is positive. On this side of the critical number, the derivative is negative. If that's the case, okay, then we say that f has a local max, right? Whenever it changes from positive to negative, like we did up here, that's a local max or a relative max. And we would say because the derivative, f prime, goes from positive to negative. Okay, so for this sine chart, we can interpret that we have a relative or a local max at whatever this critical number is because the derivative of f changes from positive to negative at this critical number. And the other scenario is, let's say our sine chart looks like this, critical number, but now we're negative for f prime and then positive. So that would be like this scenario here. Here the derivative is negative. Here the derivative changes to positive. So at this point we have a relative min. So we say f has a relative min or a local min because f prime goes from negative to positive. Okay, so this is basically what you got to look out for. So to put everything together, and we'll do this in a few examples, if you're asked to determine what the local extrema are, or to locate and discuss local mins, local maxes, you're going to take the derivative, find the critical numbers, do a sine chart, and now we're adding in finally. So yeah, last time we said the graph is increasing here and decreasing after the critical number. Well, putting 2 and 2 together now, that means that whatever this critical number is, we have a max there. And we'll be able to talk about that. And vice versa here. If we're decreasing for the function, then increasing after, that means we have a local min. Okay? So I'm going to do some examples quickly. Again, I recommend pausing so that you can try some of these examples on your own if you kind of have an idea of what to do. So find the relative extrema of f of x equals x plus 2 squared times x minus 1. Okay. So to solve, to find the relative extrema, we're going to do everything we talked about in the previous sections. We're going to take the derivative. So I would just do the product rule here. So there's f, there's g, right? So I'm going to do f times the derivative of g, which is 1, plus the derivative of f, which is 2 times x plus 2. Chain rule in here gives me a 1, so I'm not going to write it. And then we do g, which is x minus 1. Next, we could simplify it. There's a couple ways you can do it. You could factor right here, or if you're more comfortable multiplying it out, it's really all the same thing. But I'm going to go ahead and factor out, since I see an x plus 2 in common, I'm going to pull that out. So x plus 2 gets factored out, leaving me with a single x plus 2 here in the first term, plus 2 times x minus 1 over here. Let me simplify that a little more. So now this will be x plus 2 plus 2x minus 2. The 2's end up canceling, so we get x plus 2 and then 3x is what's left here. So here's our derivative, and now we set it equal to 0 to find the critical number. So first, we find f prime. Second, set equal to 0 to find the critical numbers. 3, do sine chart. 4, use x values and plug in to the original function f if necessary. So that's your basic roadmap. So do Sine Chart to determine local, min, versus max. Okay, so here's our summary. Find the derivative, set it equal to 0 to find the critical numbers. I just did that here. So if I set both of these equal to 0, I get x equals -2, x equals 0. Now, so let me highlight the steps here. So first we find the derivative. Second, we set it equal to 0 to find the critical numbers. Third, do the Sine Chart. So put -2 and 0 on a number line, and we're going to test to see what's going on with the derivative. So if I plug in something like, let's say -3, and here I'll do -1, maybe here I'll test 1. If I plug in -3 into the derivative, so here's my derivative, right? If I plug -3 in there, you get negative times negative, which is positive. If you plug in -1, you get positive times negative, which is negative. And if you plug in a +1, both of those will be positive. Okay? And so what that means then is that we have a relative max at x equals -2 because f prime goes from positive to negative. Okay? Now, the fourth part is, okay, if we actually want to figure out what that relative max is, okay, the relative max, this is part number 4, is going to be the original function evaluated at -2. Okay, so if you plug in -2 into the original function, you could see -2 plus 2 is going to be 0. So 0 times everything else will be 0. Okay, so relative max is 0. This is your work for it. Okay, but this is ultimately what we're writing. Okay, we have a relative max at x equals -2. Since that's where the derivative changes from positive to negative, the relative max is 0. In other words, the y value for the function at x equals -2 is 0. Okay, and then similarly, we can say that there is a relative minimum at x equals 0 because the derivative goes from negative to positive. And the relative max, the relative min is, let's see, plug in 0. Right, so if I go back up here to f, if I plug in 0, you get 0 plus 2 squared is 4 times -1, so we get -4. Okay, so this is what we would say. So if it says to find the relative extrema, you'd say where they're located and what that y value is. And to find the y value, you just plug in the critical number that we used. Okay, so pretty straightforward. Let's do maybe a couple more. Find relative extrema of f of x equals x squared minus 4 to the 2/3. Okay, so now we're just going to go for it. So here's the solution. Take the derivative. I'm going to do the power rule. So that's 2/3 times x squared minus 4. Decrease this exponent by 1, so now we get to the negative 1/3. And chain rule gives me 2x there. I'm going to clean things up. I still have the 2/3, but now I'm going to move x squared minus 4 to the denominator, make that a positive 1/3 exponent now. 2x stays up here with the 2. So my final is going to be 4x over 3 times x squared minus 4 to the 1/3. So there's my derivative. Now I set it equal to 0. Okay, critical numbers are x equals, so we want to figure out two scenarios, right? When does this equal 0? It equals 0 when 4x equals 0. If I solve that equation, I get x equals 0. And the other scenario, if there are any values where x is undefined, okay, we know that x is undefined here when the denominator equals 0. If I take x squared minus 4 and set it equal to 0, you're going to get plus or minus 2 for the other two critical numbers. Okay? So now let's do a sine chart. Put the critical numbers on your sine chart for f prime. And maybe I'll test -3, -1, +1, and 3. So these are the numbers I'm going to test. And I'm plugging them in here, okay? So if I take -3 and plug it in, I get a negative in the numerator. This becomes 9 minus 4, so we're going to get 5. Cube root of that is positive, so this is going to be negative. If I plug in -1, you still get a negative in the numerator, but now 1 minus 4 will be negative, so when you cube root it, that will be negative, so that becomes positive. If I plug in +1, now the numerator is positive, but it's the same story in the denominator, so that will be negative. And if I plug in 3, if you plug in 3, that's going to be positive, and so will this. So there's my sine chart. Okay? And so what can we conclude? Well, let's go ahead and actually evaluate all of these. So we're changing from negative to positive, so we're going to have a minimum here. Positive to negative, we're going to have a max here. And then we switch back from negative to positive, so we'll have a minimum there. So let's go ahead and evaluate what are these functions going to equal at f of -2, at 0, and at +2. Well, at -2, if I go back and plug it in, right? So I'm just going to write this down here so we can see. So here's the original function. If I take -2 and plug it in, we're going to get 4 minus 4, which is 0. Cube it, or cube root it, 0, squared, 0. Same thing's going to happen here. 2 squared minus 4 is 0. 2/3 exponent doesn't change anything. But now if I plug in 0, okay, you're going to get -4 to the 2/3. And so really what that's going to be is if you square the -4, you get 16. So it's the cube root of 16. Or you can, if you'd rather just leave it this way, that's fine too. Okay? So these are the values. And now we're going to summarize everything we found. So we're going to say the conclusion is f has a relative minimum at any time it changes anytime the derivative changes from negative to positive. In other words, the original function is decreasing, then increasing. Decreasing, then increasing. That happens at -2 and +2. So f has a relative min at x equals plus and minus 2, and the minimum is 0. And the relative min is 0. We found that over here, right? And the reason for that is because the derivative goes from negative to positive. So that's the first set of conclusions. The second one is that f has a relative max at x equals 0, because here we change from positive to negative. Okay, so the relative max is located at x equals 0, and the relative max is, according to this, -4 2/3, -4 to the 2/3. And this is because f prime goes from negative or positive to negative. Okay? So this is all stuff that you would, like, if this was a free response question and they want you to locate relative extrema, when they say justify, this is what they mean. Okay? All right, we'll do one more. This will be a quicker one, and this will be it for the notes. Okay, so let's say we're given the graph. So given the graph of the derivative at what x values does f of x have relative extrema? So you would get a picture. Maybe that picture looks something like this. Okay, so, and this is going to say that this is the graph of f prime of x. So the good news is we don't need to know what f of x is, right? If we're just locating the x values, all we care about are what are the critical numbers and what's going on with the derivative. And so we can say that based off of this graph, the critical numbers are, this is when the derivative equals 0, right? So anytime this derivative hits 0, so right here at -3, 0, and 3, this means that x equals plus or minus 3 and 0 are the critical numbers. Okay, so right here. So when f prime of x equals 0, we get x equals plus or minus 3 and 0, and those are the critical numbers. So put those on a number line just like we did before. And now remember, what we care about is the derivative positive or negative? So let's look at -3 to the left of it. Looks like we're above the x-axis. So that's going to be positive. From -3 to 0, we're below. From 0 to 3, we're back above, so that's going to be positive. And actually, we're going to be positive again from 3 to 0. Whoop. This should be a 3, obviously. Okay, so critical numbers are wherever the derivative is 0, so that's at -3, 0, and 3. Put those on a number line. And now we use the graph to determine, is it positive or negative? So anytime the graph is above 0, that's going to be positive for the derivative. Anytime the graph is below, that's negative, and so on. Okay, so then from there, we can now say that f has a relative max at x equals -3 because the derivative goes from positive to negative. And similarly, f has a relative min at x equals 0 because the derivative goes from negative to positive. Okay? And even though this is a critical number, there's no change here. It doesn't change from positive to negative or vice versa. So 3 does not give us a relative min or relative max. So this would be it. Okay? All right, so that is the first derivative test. So when they ask you to use the first derivative test to find local extrema, that's what we mean. Find the derivative, set it equal to 0 so you can find the critical numbers. Test, do a sine chart so you can test what's happening with the derivative. Once you know what's happening with the derivative, then you can use this to interpret where the relative min and max are going to be. And if you need to find the relative min and max, you can plug in -3 and 0 into f. And obviously here we didn't know f, we just wanted to talk about where these values were located. Okay? All right, that's it for the notes. We'll see you guys next time.